In this presentation, I am going to explain the working of phase discriminator or Foster Seeley discriminator. We know that the function of FM demodulator is to change the FM or frequency modulated wave into the ordinary modulating signal. That is, we have to convert the frequency variations into amplitude variations. The earlier methods or the basic methods for FM demodulation are slope detector and balanced slope detector. The basic concept of functioning of a phase discriminator is the same as that of slope detector and balanced slope detector. And this concept is that at the output of the circuit, we intend to get the S-shaped frequency response. The meaning of S-shaped frequency response is that the output of the output voltage of the circuit is directly proportional to the frequency of the incoming signal. So we can say that in slope detector or balanced slope detector or the phase discriminator, the output frequency response is S-shaped. This is the basic concept. So in order to fully understand the functioning of phase discriminator, it is better to understand the basic functioning of slope detector and balanced slope detector. Though the basic functioning of phase discriminator is the same as that of slope detector, but in this case, the shortcomings which are associated with the two earlier methods of FM demodulation have been removed. The shortcomings of slope detector and balanced slope detector is that in those circuits there are tuned circuits, and in each of the circuit the tuned circuits have to be maintained at different frequencies. For example, in slope detector, the primary and secondary tuned circuit of a transformer have to be maintained at two different resonant frequencies, and in balanced slope detector, the primary and secondary tuned circuits have to be maintained at three different resonant frequencies. So in any circuit, it is very difficult to maintain the primary and secondary of a transformer at different frequencies. But in phase discriminator, this shortcoming or this complexity has been removed, and as we will see in the next slides, in this method, the transformer primary and secondary are tuned at the same resonant frequency, and this is a simplified method of getting the modulating signal out of the FM modulated wave. This is the circuit of phase discriminator or Foster Seeley discriminator. In this circuit, L1C1 is a tuned circuit of the primary coil, and L2C2 is the tuned circuit of the secondary coil. As I have mentioned earlier, both these tuned circuits are maintained or they are tuned at the same resonant frequency, that is the carrier frequency or the central frequency. Let us say this frequency as Fc. Now there are certain conditions which are imposed on the values of circuit components. For example, the resistance of the load resistors R3 and R4. The values of resistances R3 and R4 are very high in comparison with the capacitive reactance of C4 and C. That is, if we compare the resistance R4 and the capacitive reactance of C4, then R4 is very much higher than the capacitive reactance of C4. Now, if we consider the circuit arm C, L3 and C4, then we can say that since R4 is very high, so the current which is passing through this uh, circuit arm will not go through R4 because its value is very high and it will proceed towards C4 only. Therefore, we can say that R4 can be taken as the open circuit and the circuit arm C, L3 and C4 is directly connected to the ground. Or we can say in other words that this circuit C, L3 and C4 comes directly in parallel with the primary circuit, as it is also shown as figure 1 of slide number 4. If C, L3 and C4 comes directly in parallel with the primary circuit, therefore the voltage V12 is directly applied to this circuit arm C, L3 and C4. And we know that the capacitive reactances of C and C4, these values are very small. Therefore, the entire voltage V12 will appear across the inductor coil L3. Hence, the voltage across the inductor coil L3 is V12, that is the primary voltage. Now, the voltage V12 is appearing across the primary coil, and due to this primary voltage, a current Is is flowing in the secondary coil. When this current flows in the secondary coil, some secondary voltage is produced. First, let us see what happens at resonance. At the condition of resonance, the inductive reactance of the circuit becomes equal to the capacitive reactance, and the circuit, which contains resistance, inductance and capacitance, becomes purely resistive. So we are considering the position or condition of resonance. Therefore, the secondary circuit and the primary circuit, they become purely resistive. Therefore, when current Is is flowing through the circuit and voltage V12 is producing the secondary current, and we know that through a resistive circuit the voltage and the current are at the same phase. Hence, the secondary current Is and the primary voltage V12, which is producing the secondary current, they are in the same phase. Hence, the voltage V12, which is produced across L3, and the current in this secondary circuit, that is Is, they are in the same phase. Now let us focus on the current through the secondary coil. As the current Is is flowing through the secondary coil, and this is pure inductor coil. We are not considering a circuit containing capacitor and inductor and resistance, but we are only considering the secondary coil. When current Is is flowing through the secondary coil, then it produces a secondary voltage. And this secondary voltage is, suppose it is VAB. And the voltage across an inductor coil leads the current by 90 degree. Therefore, the voltage VAB is 90° ahead in phase to the current IS through the secondary coil. Hence, the phase difference between VAB and IS is 90°, and voltage across L3, that is V12 and IS are also in same phase. Therefore, the phase difference between VAB and V12 is also 90°. Now let us concentrate on the upper circuit, that is the circuit containing the diode D1. Two voltages are applied to the diode. The first is half of the secondary voltage, that is half VAB, and the voltage across L3, that is V12. The phase difference between V12 and half VAB is 90°, and the resultant of these two, let us say it is VAO, and it is shown in figure B of slide number 4. The net voltage applied across diode D1 is VAO. Similarly, if we consider the lower circuit containing the diode D2, then the diode D2 is getting voltage V12 and minus half VAB, and the resultant of these two voltages we have shown as VBO. VAO and VBO, as shown in slide number 4, they both have the same magnitude, but they are in opposite direction, or we can say that the voltage VAO and voltage VBO are of the same magnitude. Hence, they will produce the same current through the diode D1 and through the diode D2. Both the currents are same, but the direction of current through diode D1 is in clockwise direction, and the direction of current through the diode D2 is anti-clockwise. Hence, the voltage which is produced across the load resistor R3 and the voltage produced across the load resistor R4, they are of the same magnitude, but they are in opposite direction. Hence, when we take the total voltage across the output, then these two voltages will cancel out each other, and the net voltage at the output will be 0. Or we can say that the output voltage at resonant frequency will be 0. Now let us say what happens when the frequency is above the resonant frequency. Let us see what happens when the frequency of the incoming signal is greater than the resonant frequency or the central frequency, that is Fi is greater than the central frequency Fc. We know that in any circuit which contains inductance, resistance and capacitance, when the frequency of the signal is greater than the resonant frequency, then the inductive reactance is greater than the capacitive reactance. Or in other words, we can say that the circuit starts behaving as an inductive circuit. So in this case also, when the incoming frequency is greater than the resonant frequency, the primary and secondary circuits will start behaving somewhat like the inductive circuit. In an inductive circuit, the current lags behind the voltage which is producing it. Therefore, we can say that the secondary current Is, which is produced by the incoming by the primary voltage V12, that will lag behind this current Is, or the secondary current will lag behind the primary voltage V12. In the case of resonance, IS and V12 were in the same direction or we can say that there was no phase difference between IS and V12. But in this case, since the circuit is an inductive circuit, therefore the secondary current IS lags behind the primary voltage V12 by some angle. But the voltage VAB, this is the secondary voltage. The secondary voltage is produced by the secondary current IS passing through the inductor coil. Therefore, the voltage VAB across the secondary coil leads the secondary current IS by 90 degree. That is, the angle or the phase angle between the voltage VAB and IS is 90 degree. We can see from the figure that the net result is that this vector VAB is slightly turned in the clockwise direction, in this direction, due to these developments, or we can say that the angle between half VAB and V12 is slightly decreased in comparison with the earlier case, and the angle between V12 and minus half VAB is increased. Okay, so this angle is decreased and the lower angle, this angle is increased. As a result, the resultant voltage VOA, this voltage in the upper circuit is increased, and the resultant voltage VOB in the lower circuit is decreased. This is the voltage VOA is the voltage applied across the diode D1, and VOB is the voltage which is applied across the diode D2. When the voltage in the upper circuit or upper diode is higher, therefore the current will also be greater in the upper circuit, and since the voltage VOB is smaller, that is the voltage across D2 is smaller, so the current in the lower circuit will be smaller. Hence we can say that the voltage across the load resistor R3 will be greater, and the voltage produced across the load resistor R4 will be smaller. Since the output voltage is voltage across R3 minus voltage across R4, hence for frequency Fi greater than resonant frequency Fc, the output voltage is positive. Hence, when the frequency of the incoming signal is greater than the resonant frequency, then the voltage becomes positive, and as the frequency increases, the output voltage increases in proportion to the incoming frequency. Similar is the case when the incoming frequency is smaller than the resonant frequency. In that case, when the frequency is smaller than the resonant frequency, the circuit starts behaving as the capacitive circuit. And when the circuit is capacitive, then the current leads the voltage, that is the secondary current will lead the primary voltage, hence the vector half VAB will shift in the anti-clockwise direction, or the angle between half VAB and V12 will be slightly increased, and angle between minus half VAB and V12 will be slightly decreased. Hence, the voltage across the upper circuit or the upper diode is decreased, and the voltage across the lower diode or the lower circuit will be increased. So we can easily make out that in the output load resistor, the voltage across R3 is smaller and the voltage across R4 is greater. Hence, the net output voltage, which is equal to the upper voltage minus lower voltage, will be negative. Hence, we can say that when the frequency is less than the resonant frequency, then the output voltage is negative, and as the input frequency is decreasing, it increases on the negative side. So we can say that the output frequency response of this phase discriminator will be S-shaped as was required when this circuit was designed.